This stands for Beery Neumann stable invariant. And I will say a few words about applications and some applications. This talk is okay. The application part is based on my joint work with two people, Daciberg Lima Gonsalves and Ralph Strabel. So, and let me begin by saying that this whole talk is concerning finitely generated groups which are typically infinite. The whole theory will be sort of uninteresting, or if the group is finite. But I suppose that this conference is mainly concerning, our workshop part is mainly concerning finite groups, so I apologize for that. But I do hope that there are interesting things happening also about infinite groups. So, this Beery-Neumann stable invariant is actually a topological space associated to a group. I'm basically a topologist, and we are used to studying topological spaces by associating invariants which are like fundamental groups and so on. So now the table has been turned around, and now you start with a group, typically infinite, and then to that we associate a topological space, and we try to understand the group by looking at the topological space. So the first time I came across such a situation, of course we are used to associating Kaly graphs and so on, which may be thought of as topological spaces, but this is really an invariant. So let me first tell you how this invariant is defined. So let G be a finitely generated group. So, yeah. So by a character, what we mean is so a character chi is a homomorphism from G to R. Typically, a character should mean that you have homomorphism from G to C star, or maybe you should expect R star, but R star means positive and negative real numbers under multiplication, but you forget the negative numbers, just only keep positive real numbers, but then that's isomorphic to the additive group of whole real numbers. So you look at it this way. So this is what we mean by a character. And it turns out that, of course, you have this space, space of all characters form a vector space, and this is going to be finite dimensional because the group is finitely generated. Okay, and now what you do is you remove origin out of this, so you get a character sphere. So the SG equal to, just look at this vector space, remove origin out of it, and consider the relation where two characters are related if one is a positive multiple of the other. Okay, so this is just if you are looking at it as a vector space, all rays emanating from the origin. Of course, that's up to, I mean, it is homeomorphic to the sphere S n minus 1, where n is equal to rank. rank of the abelian group G mod the commutator subgroup. Okay, because this vector space has dimension equal to G mod the abelianization, that is G mod commutator subgroup. So now the main motivation for considering the invariant, I have not even started on the definition of BNS invariant. It was to understand, suppose you take a finitely generated group, the commutator subgroup need not be finitely generated. For instance, you can take the free group. Now you would like to know whether it can be finitely generated when you think of it as some object operated upon by a certain submonoid of this. So let me now define this. This is the BNS invariant. Sigma of G is so set of all character classes, that is rays, or points in the character sphere, such that, well, GG is finitely generated over a finitely generated submonoid of, well, you have the character, so I have a homomorphism from here to here. I just look at non-zero, non-negative real numbers, look at the inverse image of that. Okay, so this we may call G chi. It's a fairly complicated definition, but I'll explain. So if you look at a submonoid of just the monoid of all non-negative real numbers and look at the inverse image, that's going to be a monoid. You don't demand that this itself must be finitely generated over this. That would be a more natural thing to do. But actually what they did was they say that the invariant you associate consists of precisely those character classes such that the commutator subgroup is finitely generated over a finitely generated submonoid of this. So it's quite a complicated type of definition. Okay. Notice that it doesn't depend on the representative. If I change this by some other thing, character equivalent to that, this G chi doesn't change. So G chi depends only on the character class. Okay. All right. So one immediate example is if G is abelian, okay, say Z power n or something, then of course the commutator of that is trivial, and of course then Sg is equal to the whole sphere, sorry, sigma G. And if you take the free group, non-abelian free group, then this is empty. No, they don't. Yeah, it could so happen that the character class belongs to the invariant, but the negative of that doesn't belong. Yeah, that's why you need to in fact work with the sphere. So I didn't explain here, write it out. So two characters, chi is equivalent to chi prime. If chi prime is equal to r times chi with r positive is extreme. It's important that you work with only rays. The sphere rather than with the projective space. There is another definition. Actually, this was introduced around 1987. At least a paper was published around 1987. There was another definition given in the same paper in terms of what they call kite track and so on. I mean, sort of more equational type of definition. But that one, it was later observed that that same definition can be recast in terms of the Kaly graph. So I will give a definition now, which is in terms of the Kaly graph of the group. So I don't know if I should explain the definition of Kaly graph. Perhaps everybody knows. In any case, so you have to fix a finite generating set. So let us fix X, a finite generating set for G. We'll assume that X is equal to X inverse. Okay. Symmetric. So the graph will have vertices equal to the elements, members of G, and two elements, G and G dash are joined if you can write G dash as S times G, where S is in X. So this is a Kaly graph. So suppose I look at the Kaly graph of G with respect to X. Then I can get a subgraph of this by looking at this. So the subgraph is denoted gamma chi is equal to those with vertices precisely in this G chi subgraph of the full subgraph of the Kaly graph of CGX with vertex at this G chi. So let this be the case. Then this is in sigma G, BNS invariant, if and only if this graph is connected. You have to show several things, that it is independent of the set X used for the definition and so on, but it turns out that this is the case. Okay, so this gives you a better, at least pictorial way of understanding what is happening, and in fact this definition is much more pleasant to work with. There is another generalization. For want of time I won't talk about that, but this definition is due to Brown, Kenneth Brown. His definition allows you to describe this phi of G for any group, not necessarily finitely generated. Not necessarily finitely generated. And of course, you need to look at things in a completely different way, not in terms of looking at characters and so on. Characters will enter into the picture naturally. The route taken by the definition of this involves non-trivial abelian action of the group G on real trees. So you have a group acting on a tree or real tree, then you have associated to any such thing the length function. You say that it is non-trivial. The action is abelian if the length function is given by So length of each element you can talk about. Length of this is equal to absolute value of some character chi from G to R. So that's the notion of an abelian action of a group on a length on an R tree, and then there is a notion of non-trivial action. So it requires a little, some more technicalities, some definitions to explain this, so I will not do that. But the important thing is that this definition works even if you do not assume that the group is finitely generated. So group can be infinitely generated, anything. Gamma chi is a subgraph. No, the full subgraph. Okay. The full subgraph of this with vertex set equal to this. Okay. The difficulty with working with this BNS invariant is that it's extremely difficult to compute. The paper of Beery-Norman-Streiber gives a lot of examples, some coming from three-manifold theory and so on. I will state some results of that paper, and then I will talk about the application part. Okay? I have plenty of time. So let me state one theorem which is already there in BNS paper. Suppose that G is finitely generated, finitely presented, and contains no non-trivial, non-abelian free group. Infinite, finitely generated, finitely presented, infinite, contains no abelian free group. Then it just says something about how sigma is equal to, it is sort of symmetric. Okay. It says how this is. I forgot to mention even before this the main theorem about this one. So let me just state that. Before this theorem, I should have stated that. So what kind of a subset is sigma G? The theorem. So G finitely generated. Then this is an open subset. Open subset of the sphere SG. So that's the main theorem. It's a main theorem of this. And then what type of set, what type of open set it can be? For example, if G is finitely presented and contains no non-abelian free group, then it is sort of symmetrical. So this minus means antipodal map in the sphere. Okay. Character goes to minus chi. So suppose that, suppose say, Y is an n-dimensional compact manifold. Smooth manifold. Then you see you can think, so and G is equal to pi 1 of Y. You can think of a homomorphism from G to R, homomorphism. This can be thought of as an element of the first cohomology group. So you can think of chi as an element of H1 Y with coefficients in R. And to this Y, you can associate the following subset. Chi Y is equal to set of all set of all classes in the sphere G. G is the fundamental group of Y. Those classes which are represented by such that chi, you can see, because it's an element of first cohomology, then you can think of this therefore as defining as being defined by a smooth one form, okay? And that smooth one form, you just require it to be, suppose, so viewed as a, okay, let me say this is represented by a nowhere vanishing smooth one form on G, on M, on the manifold Y. Okay. Of course, if chi is represented by it, so is minus chi. And so you see that sigma of Y is equal to minus of sigma of Y. Then theorem is that, okay, sigma Y is equal to sigma, okay, let me just write that. Sigma G, if Y is yes, three manifold. Stated also for three manifold without boundary and with boundary, doesn't matter. So I think there's some condition. No, sorry. I think there's some, sorry about that. This is not quite what I wanted to say. Suppose that I missed out one thing. So I should correct myself. This is a homomorphism. All this is okay. Let me say this following thing. Suppose that chi is a character which takes values in here. So G to Z. This is important. Okay. Then, so it is what is called a rank 1 character. It's not just an arbitrary homomorphism. it is a homomorphism whose image is an infinite cyclic group, then chi, this statement is for rational characters. This is the case, then dimension equal to 3. Equal to 3. Then chi, class of chi is in sigma g, if and only if chi belongs to sigma of y. Okay. G is pi 1. Yeah. This is equal to pi 1. So, this allows one to describe the shape of sigma g. So, suppose that y is 3 manifold. Let's just say close 3 manifold. Then g is equal to fundamental group pi 1 of y. Then sigma of g is a finite union of open rational polyhedral group. Rational polyhedral subsets of polyhedral group. Well, polyhedra, okay, subsets of the sphere SG. So, in other words, so polyhedral subset means you must think of it as sort of intersections of rationally defined spheres. So, you see, you can make sense of rational points in the sense that instead of looking at homomorphisms from chi to R, just look at homomorphisms from G to rational numbers. So, that way you get a rational structure on the vector space, and your polyhedral means just intersection of finitely many. You can either do it in the vector space and intersect it with this and look at the image in the character sphere, or directly just look at hemispheres defined rationally and take finitely many of them, look at the sort of half spaces and intersections, and that will be rational polyhedral cones or polyhedral subsets of this. And you always have to look at open rational polyhedral subspaces. This is just a finite. And one other condition also, sigma union minus sigma is equal to the whole of the SG. So, this also is an important consequence. At the time of their paper, Poincare conjecture was not proved. So, they had it for a slightly restricted class of, they had to make some assumption about this one. But now that we know Poincare conjecture is valid, so I didn't bother to make a this precise statement that was proved in that paper. Okay. So, I have about 15 minutes. I want to give one other example, other application of this. So, all this is already there in the BNS paper. there is one other example that is also contained in the BNS paper, and that is the following. So suppose that G is a finitely generated subgroup of piecewise linear homeomorphisms, orientation preserving. Okay, I just write orientation preserving piecewise linear homeomorphisms of 0 to 1. You could have any positive number here, doesn't matter. So an element of this will have a graph looking like, something like this, or maybe something like this. So typically like this. Then you say we need two definition. G is irreducible if G does not fix any point of the open interval 0, 1. Of course, everything fixes the endpoints. When you have a group like this, there are two obvious homomorphisms. I explained that. They may be called chi0 and chi1. So what is chi0? Chi0, so you take any, this is a homomorphism from here to here, so is chi1. Chi0 of a piecewise linear homeomorphism, you just look at the first direction along which it takes off. So I'll just briefly write this as phi prime, f prime 0, slope at 0. Okay, that it has to be defined appropriately, but we understand what it means. And chi1 of f is equal to slope at 1. And these are homomorphisms. Actually homomorphism to the multiplicative group. So in order to make it additive, I should take log. Okay. Now you demand this following property. We say that chi0 and chi1 are independent characters. Independent. So this is about just characters of any group, not necessarily this one, and chi0 and chi1 can be any characters. You say that they are independent if chi0 on kernel of chi1 is equal to chi0 of the whole thing, and also the other way around. Chi1 of kernel of chi0 is equal to chi0, chi1 of the whole thing. So what it means is that slope at this point, whatever that number is, okay, of a particular element, you just look at here. It may not be that slope here is equal to 1. In other words, chi0 may not be 0 there. But you see, chi1 may not be 0. But you can realize the same slope for possibly some other element of the group where it is actually identity near that. Okay? And if that happens, then such an element will belong to the kernel of this, and chi0 of the kernel, such an element is already realized as chi0 of the one that you had previously. So this sort of says that the two characters in some sense are independent. I want to emphasize that it has nothing to do with linear independence of characters in the vector space, okay, that we had. Nevertheless, it's a very important property. Now we can state the theorem that is there in that paper. Theorem, BNS. So if G contained in orientation preserving PL homeomorphisms of the interval is irreducible, and chi0 and chi1 independent, then the character sphere, okay. Then actually let's look at the complement, it's much nicer to describe. The complement of the BNS invariant associated to G consists exactly of 2 points, namely chi0 and chi1. Okay. So this is an important thing, and the interest in this one is that, you see, it is difficult to give examples of see here you always had this rational polyhedral cone. So if you look at the closure of these ones, they will contain sort of rational cones or rational polyhedral spaces where the vertices are all rational. But such a thing is not always the case. So they wanted to illustrate it by means of this example. So in other words, typically chi0 and chi1 homomorphisms may not take values in integers or rational numbers. So let me now come to the part that is where we use BNS invariant to a certain problem in group theory. I have 8 minutes, so I'll explain the problem and then tell you what is the result. So, okay, so now this is a different problem altogether. You look at the following situation. So suppose that G is an infinite group. Phi is an automorphism from G to G. And so you have this notion of twisted conjugacy. You say that X is phi twisted conjugate to Y if there exists a G in G such that X is equal to G, Y, Pg inverse. Okay. So if phi was identity, this would be usual conjugacy. And now we have twisted that by phi. Okay. This is what is called twisted conjugacy. There is this following notion. You look at R phi, the cardinality of twisted conjugacy classes. Phi twisted conjugacy classes. Now, you say that the group R has group G has R infinity property if R phi equal to infinity for all phi in the automorphism group. Okay. So this notion came up, originated in fixed point theory. R stands for Reidemeister. Okay. It has very interesting relations with the Nielsen fixed point theory and so on. I don't have the time to go into that. I just want to give you one example. Suppose you had, for example, so z power, okay, z, and look at z to z multiplication by -1, then Reidemeister number of this is equal to 2. So z doesn't have this property. And you can even do this for z power -n, and then you can count it actually. But this is finite, I think 2 power n. Whereas if you look at this Klein bottle group, for any phi, R phi is infinite. So this behaves very badly even if you just slightly change the group, meaning Klein bottle contains a torus group Z power 2. For Z power 2, R infinity property doesn't hold. For this, R infinity property holds. Okay. So let me just say, connect up these two. So suppose you have G is a group such that, and you have a character, well, some homomorphism to some abelian group Z power k, such that chi composite with any phi. Phi star chi. So just phi any automorphism. Okay. Phi auto G. If it turns out that this is equal to chi for all chi, for all phi, okay, then it's trivial to see that yeah, R has G infinity property. Okay. Now, that means that what you are looking for is something okay. So what you would like to do is search for characters which are fixed by automorphism. Now, when you have an invariant such as BNS invariant, that's the right place to search for characters fixed by all automorphism, because you see the character sphere, out of the character sphere you have a certain subset which I said is an invariant, and therefore it must be any automorphism of the group should induce a homeomorphism of the sphere. Suppose you are able to find a fixed point in that homeomorphism, then what happens is you have found not a character but a character class. So BNS invariant sigma G, okay, under certain conditions. See, there may be automorphism which does not admit any fixed point for here. You may not be able to find a fixed point. Suppose that this is such a nice thing that you are able to find a fixed point. For instance, I have a situation where the complement had exactly 2 points here. Okay, so suppose I have an automorphism. That automorphism is going to preserve sigma G, and therefore the complement of sigma G also. So it could either keep this, I mean, as identity or flip. Okay, and but there is a catch. Now it involves character classes, whereas we really need a genuine character. Okay. Now, if you forget that problem for a minute, then it is clear that BNS invariant can be exploited to say something about the R infinity property, and this is what we did in our paper, which is going to appear in the Pacific Journal of Mathematics. It's myself, Gonsalves, and Strabel. The step from obtaining a fixed point for the automorphism to fixed point of that fixed point being a character class to actually getting a character involves, for the situation that we were in. What was the situation we were in? We were looking at various groups, subgroups of the PL homeomorphisms of the interval orientation preserving, and there we imposed certain condition which ensured that if a character class is preserved, then the character itself is preserved, and that step involved some invoking some results from number theory and so on. I don't have the time to talk about it. I'm just out of time. I will conclude by saying that among the groups that we considered, and I'll just take at least 1 minute to state what type of groups were considered so you understand. There is this famous group called Thompson group, F, which is consists of all those PL homeomorphisms of the interval 0 to 1, where the slopes are powers of 2, okay, and the breakpoints, where there are points of non-differentiability, they are all dyadic rationals, okay, and that group was settled by or infinity property for this group was known prior to us. It was proved by some 3 people, Colin Bleek, Gonsalves, and Feldstein. But there are generalizations of these groups, and they pose a lot of difficulties. These are the groups, Brown, Higman. I can only just give names. Brown, Higman, Thompson. This is Richard Thompson groups. So they just to take parameters n1, n2, you can just assume that they are pairwise relatively prime. And then what is this group? This group consists of all those which have slopes in the multiplicative group generated by n1 to nk. And slopes in the, the breakpoints will be those which can be written as some m by something, some number, or where r involves only these n1, n2, nk to appropriate powers in the denominator. So using our methods, we could prove that these groups have the R infinity property. Okay? And we considered many other families, but I don't have the time to talk. Thank you. Yeah, that's right. So it's just, you can forget about this. Suppose there is a chi. Suppose there is a chi such that this is the case. So I didn't write full sentences. Suppose there exists chi. Yeah. What is it? So you can just take, a polyhedron is an intersection. Let's just do it at the level of vector spaces. Polyhedron is an intersection of half spaces. Okay, finitely many half spaces. And then you remove the vertex and look at its projection. That is what I call polyhedral subset. And rational means these planes must have rational equations. There's a rational structure in the vector space. Okay, that's what I mean. Yes. Yes, I think that's easy to see. For automorphisms, it's easy to see, but yeah, in fact, it's not at all. Because if you look at the very first definition, that did not involve any generators and thing. Yeah, if you use it that way, then probably it is not so easy because, yeah, I'm not so sure. Yeah. No, even there, I think the Kaly graph will map one to the other in an isomorphic manner because you have fixed a generating set. But it is easy to see for automorphisms, definitely, that it's there. You just look at the original definition. Yeah, finite. Yeah, for right-hand Coxeter groups, yeah, Artin groups, they have been studied. Yes. Yeah, there are, but the computations are difficult. So that is probably one of the reasons that the BNS invariant is not very well known. I sort of like to advertise that.